Good morning, good afternoon everybody. Welcome to the next session on audio coding. So last time we saw the modified discrete cosine transform, right, the MDCT, how it's defined and how we implement it using polyphase matrix and this matrix decomposition of the polyphase matrix. And we found we can improve the MDCT even further if we extend the length of the MDCT. And it's also desirable to be able to extend the MDCT length without increasing the system delay. Because usually the longer we make the filter, the more delay we have, but often this delay is not desirable. So this is what we want to talk about next. So we can extend the length of the MDCT and obtain longer filters if we have higher order polynomials in our polyphase matrix. Because the polynomial order determines the number of blocks that we have in our impulse response. And that means if we want to have longer filters, that means we have more blocks in our impulse response, and that means we have higher order polynomials. And to obtain perfect reconstruction, we want to have easily invertible matrices for that. So the approach that we take is we take the MDCT polyphase matrix and multiply it with easily invertible matrices with polynomials of first order. So that basically increases the order of the resultant polyphase matrix by 1. So we have an order of 1 higher, and that means we have 1 block more in our impulse response names. So if we have like block length n equals 1024, that means we increase the filter length accordingly by 1024 samples, which is quite considerable. So, and then to control the resultant system delay, we need to design with different matrices with different needs for a delay to make them causal. And we saw that this was the cause of the system delay in the MDCT, that we have the delay matrix, and the inverse of the delay matrix needed to be multiplied with z2 minus 1 to make it causal, because it has a z2 plus 1 in the entries. So we start with a polyphase matrix of an MDCT, HMDCT. And then we multiply this polyphase matrix with some matrix L of Z, right? And this should be a matrix of first order. And you can read more about it in one of our early papers from around 2000. So this matrix L needs to have a form such that we again obtain a modulated filter band. So we want to keep this diamond-shaped form for the resulting filter matrix. Right. So this needs to be maintained, otherwise we don't get a cosine modulated filter band. So this is an example that fulfills those requirements. Right. We have again ones on the alter diagonal of our matrix. The empty spaces here are filled with zeros, and then on the first half of the diagonal we have delays multiplied with coefficients L, right, as you can see here. So it's only one half of the diagonal, then the anti-diagonal is ones and the rest is zeros. And this is what we call a zero delay matrix. And why do we call it zero delay matrix? Well, you can see when we look at the inverse is this. And the inverse simply consists of the same entries, but with a diagonal flipped to the other side and with negative signs. Right? So you can see here that here the sign of the entries are changed, so the signs are changed, but not the exponent sign. The exponent is still minus 1. So unlike in the delay matrix where we change the exponent for the inverse, here we only change the sign of the coefficients. And this means we don't need to multiply it with a z to the minus 1 to make it causal, because it already is causal. Right? So this is convenient. So this means we increase the filter length, but we don't need any additional delay. We keep the delay as it was before. So this is one of the big advantages. Yeah, so since the matrix has a causal inverse, we can increase the filter length of the resulting filter length without increasing the system delay. So this can also be seen of looking at the transfer function and just adding zeros inside the unit circle. So basically like a minimum phase system. So the coefficients h of n from the MDCT polyphase part and L of the zero delay matrix don't affect the delay or the perfect reconstruction property. Right? It's all invertible with a given system delay, but they influence or they determine the frequency response of the resulting filter bank. Right? So the structure of the matrices give us the system delay and the perfect reconstruction, but the coefficients determine the frequency response. And this is, again, still an essential part of filter banks, right? Because we want the filters to be good, narrow band and having high stop attenuation. So these coefficients are then found by numerical optimization. So fortunately, Python has quite good optimization packages or functions, so we could just formulate an objective function which captures the quality of our desired or of our obtained frequency response, and then we just minimize this objective function. So this objective function could, for instance, be the error in the pass band and the stop band compared to ideal filters. Right. So now we can also do the opposite. Instead of having zero delay, we can now also get a maximum delay matrix. And we do that by just inverting the time scale or the time axis. Instead of z, we have z to the minus 1 in the arguments. So here we take L of z to the minus 1, and since we have the inverse of the argument in the matrix, we get z to the plus 1 in this matrix, and hence we need z to the minus 1 to make it causal. Right? And the same for the inverse. Right? So the inverse here is still the same as before, but since we replace z by z to the minus 1, we need to have this z to the minus 1 to make it causal. And in total, matrix times inverse matrix hence needs two delay elements, hence we get z to the minus 2. Right. So over analysis and synthesis we get 2 blocks additional delay to make it causal. Right. So in effect we increase the length of the impulse response by 1 block of n samples, capital N samples, but we increase the delay by 2 blocks. So we delay the system delay even more than we extend the filter length. Yeah, so 2 blocks. And this can also be seen as adding zeros only outside the unit circle of the z-domain representation of the transfer function. Right? So it's kind of, instead of minimum delay, minimum phase, it's maximum phase. Yeah, so for the design of filter banks, we can now choose what we want to have. So we can determine the total number of zero delay matrices and maximum delay matrices according to the desired total filter length. Then we can determine the number of maximum delay matrices according to the desired system delay, because only the maximum delay matrix change the system delay. Yeah, and then finally we can determine the coefficients of these matrices with numerical optimization to optimize the frequency response. Right. So here I have a little example which I can show you, where we actually implemented those matrices. So I can show you. So I just open an editor here. Copy. And open. There we go. Gedit. Paste. So here's now the Python example for it. So in the beginning, you can see again, same as what we already saw the last few times, import PyAudio, struct for conversion from binary to integer, NumPy, Matplotlib, CV2 for live displaying of our waterfall diagrams, and here FFTPEG for the DCTs. Then we import FrexZ to display frequency responses of our filters. And time is not so important, it's just for measuring the time for functions. So then we go on with the filter. So first I have a function which initializes the memory for the filter bank. So each z to the minus 1 is a memory element. Right? It stores an integer, it stores a float number until the next clock cycle, until the next sampling cycle. Right? We have sampling cycles, the lower sampling rate here is the block sampling rate. So here those memories are for implementing the z to the minus 1. They keep one float sample until the next sampling cycle. So we just need to set them up, initialize them with zeros. This is also important if you want to run a filter bank several times. Before you run it the next time, you want to make sure that the memory is 0, right, in order to avoid artifacts. Yeah, then here's the delay matrix, which we already saw last time. Can you see it from the back, the front? No? I guess you need sharp eyes. Yeah, maybe. So, references, fonts. Okay, so now it's a little darker. So here we see the D matrix, which basically stores the delayed values, the upper half of the diagonal, corresponding to the first half of our block. It stores them for one sample cycle in dmatrix.z and passes the second half of our block, corresponding to the lower half of the diagonal, directly to the output, which you can see here. So this is the D matrix, which we already saw last time. So the D inverse matrix does the same thing, but now it just delays the second half of our block by one sample cycle. Here is the F matrix. Here I implement the multiplication of the F matrix directly with array multiplication of the coefficients. So this is a slightly faster implementation. So instead of using matrix multiplication, I'm directly multiplying coefficients according to this diamond shape. So nothing complicated, it just looks a little more complicated. So then I have the inverse of it. And here we see the low delay or the zero delay matrices. So they're implemented basically the same way as the delay matrix D. So the anti-diagonal matrix means we flip the input, and the first half of the diagonal, which is delays times coefficients, means we delay the first half of our block and multiply it with the corresponding coefficients, and then add it to the output. Right? And this is what you can see here. We have our samples here, and then we have the delayed samples, the first half of the block of the previous block, which is in here, times the coefficients. Right? So coefficients equal coef here as part of the argument is passed from some other function, and then we just add it. And yeah, and here out equals samples, colon, comma, minus 1 is the flipping. Right? So this flip left, right. So basically means the array from the beginning to the end, but with step size of minus 1. So that basically reverses everything. So this is just a trick for flip left, right. The same thing, and I think it's slightly faster. Yeah, so this is doing the anti-diagonal stuff. This is the delays of the first half of the coefficients from the last block. And here you can see the G matrix now gets the first half of the current block to be used in the next output. Make sense? So output is flipped input plus multiplied first half of the previous block. Then here we have the inverse G matrix, which is doing the inverse. So now we have again flipping, right? So the antidiagonals stay the same, but now we have the samples of the second half in our memory. So the second half of our block is delayed, and then we multiply it with the coefficients and have a negative sign here. So that's exactly the inverse. So if you now apply this processing first G matrix, then G-inf matrix right after it, using the same coefficients, then we get identity. Yeah, here you can also see that the coefficients here are flipped. Again, it flipped left, right. And this is also what we see here when we go back to the formula. So here this formula. So here you can also see the coefficients are flipped. So L0 was first at the beginning, now here it's at the end. So that's why we get this flipping. So back to my editor. So same with the maximum delay matrices. Let's skip it. Here's the DCT4 matrix. So remember, this is what comes at the end of our product chain of matrices. So when we multiply the F and the G and the D matrix, then we have the DCT matrix, and this is here the DCT4. Again, not implemented as matrix multiplication, but using the fast FFT for implementing the DCT type 4. And actually we're using FFT.DCT type 3, because that's what SciPy gives us. SciPy already has a DCT type 3, a fast implementation in it, but unfortunately not type 4. So I'm using a trick here to implement the type 4 using the type 3. So here you can see it. I upsample the samples. So I have sample 0 until the end. So I have a block of twice the length. Then I apply a DCT type 3 to this double length block, where half of it is zeros. So it actually means we have a little bit more computation this way. Here's some scaling, and then since the output of the DCT is also twice as many samples, here we just need the first half. Right? So it turns out when we have an upsampled version, the spectrum, because of the sampling, is repeating. Right? And that means the first half is identical to the next half. And that's why we only need the first half. And when you analyze it, it turns out that this first half is identical to the DCT of type 4. And what's essential is that this upsampling starts at sample number 1 and not sample number 0. Because this shift by one sample gives us the shift by 0.5 in the time domain for the DCT4. Right. So this is actually essential. Yeah, so this is the trick here for implementing the DCT4, a fast implementation, eventually using inside the DCT3 using the FFT. So this is also important to make it run fast. Yeah, and then I have the complete low delay filter bank, which you can see here. So this is just a function. Input is samples, which is one block of samples. For instance, 1024 samples, if n equals 1024. And FB is the coefficients. So FB is an array of all the coefficients needed for this filter bank. Yeah, so it then starts with computing capital N as the length of our samples. So it concludes N from the number of samples. Then F coefs is the coefficients that we need for the MDCT part of our polyphase matrix. So it's the first 1.5 coefficients. So remember, we have 2n coefficients in this F matrix, but the last n over 2 coefficients can be computed from the condition determinant equal 1. Right? If we set determinant equals to 1, then the last n over 2 coefficients can be computed from the first n over 2. Yeah, and then we have the two zero delay matrices, G0 and G1, and these each have 1 over 2 coefficients. Right? Half of the diagonal means n over 2 coefficients. So the next n over 2 and then the following n over 2 go to the two zero delay matrices. Make sense? So here I'm just assigning those coefficients that we need for the filter bank. Yeah, and then I start the actual filter bank computation here in line 183. I start with the input samples and apply the symmetric F matrix and giving it the first 1.5 n coefficients. And so this multiplies to our, say, 1024 samples, the coefficients of our filter matrix. So out comes this array y. So y is now again a vector or an array of 1024 samples. So remember, this does not contain any memory. So it's just those coefficients. So it's simply based on the current block only. But next is the D matrix. So this delays the first half of the coefficients. So then the output consists of the past first half of our block, so the first half of the previous block, and the second half of the current block. Right? So this y here now contains as input 2 blocks. First half is from the previous block, second half from the current block. Make sense? So here we get time delays into it. Then next comes the zero delay matrix. So here we have y as an input. Here this is just an index for the memory elements. We need to have separate memory elements for each instance we use. Yeah.
Excuse me, could you please explain in the beginning how we define it that the previous one is 0 or how? If we start and it takes the previous one which we started right now, do we define the previous one?
No, for the previous one you have to, well, maybe I should go back to the delay matrix. So, here's my delay matrix. Here's my delay matrix. Can you see it? So the previous one is this. So D matrix Z dot Z. Z is in this case an array of length n over 2 samples. So this is a memory array, and this gets assigned the first half of the current vector. Right? So the first time you call D, this will be empty. Right? So when you call this line before, number 44, D matrix dot Z will be zeros.
Zeros.
Right? right? But the next time you call it, it contains the previous first half of the block. So you call it many times, and that's how those memory elements are filled up. So each time you call this function, this D matrix dot Z contains the elements from the previous call.
Half of the half of the previous.
Yes, right. So here you can see which half. Here, this is the first half. Right. It takes n/2 samples. I'm just wondering why there's twice an int. It looks like overkill. Well, it doesn't hurt, but I guess it's not really necessary. Yeah, so this is kind of tricky. Does everybody get it? So this works because we call this function for each block that arrives. First block arrives, we call those functions. Second block arrives, we again call those functions. And those memory elements, they keep the memory between the calls because they are global variables. Right? I initialize them here in the init function. Here. So here I initialize them. And yeah, how can we see that they are global arrays? Let me check. Interesting. Yeah, somehow they need to be defined, I guess, as global variables. Maybe in the main. Let me check. Interesting. I don't find it. So maybe search for D matrix.z. D matrix.z. Interesting. Kind of amazing that it works. Yeah, can't find it in the moment. But these are basically global variables which keep their memory between the calls. And the same principle is true for the zero delay matrices and the maximum delay matrices. So yeah, so back to the actual filter bank implementation. So now here we are at the delay matrix, and here we apply the two zero delay matrices. Again, these are the indices for the memory elements, so that we have separate memory elements for each instance of the zero delay matrix. And finally, we apply the DCT function to it, and then Y will be the output of our complete low delay filter bank. Make sense? It's actually quite easy, right? Just a few function calls. So and then the inverse, the synthesis, is simply the reverse steps. So here's the function low delay filter bank inverse. Now the input is a block of Y, the frequency domain coefficients, and FB, again, the same coefficients. So here we create the same coefficient vectors, and now we go the chain backwards. So first we have the DCT4 inverse. So conveniently, the DCT inverse is the same as the DCT forwards, except for some some factor here, then we apply, now as first 1 and then 0, the inverse matrices, the inverse zero delay matrices, then the inverse delay matrix, and then the inverse F matrix. And finally, we return the X, which is the reconstructed array X, now the time domain block. Right. So how much delay now then do we have from analysis to synthesis? So which X is returned here? So we have a sequence of X vectors going into analysis, and we have a sequence of X vectors coming out of the synthesis. What do you think? How much delay? When does the first block of X's come out from the synthesis? After how many steps? 2? 3? Well, think about where did we need to have a delay to make it causal? Well, we had it with a delay matrix, right? So only the delay matrix in this chain here, where is it? This one here? This D inverse matrix needed a delay to make it causal. Right? This was the only one. So that means this D-inf matrix function inherently has a delay by 1 block built in, because it needs to be causal, right? Otherwise we couldn't implement it. And this is the only one, right? The other ones are exact inverses. They don't need to have any delay to make it causal.
So we need to add additional artificial delay, so it works, and it's not 1.
Yeah, so, right. To make this causal, we need to have an additional delay by 1 at the lower sampling rate, which means 1 block delay. Right? The lower sampling rate is the block rate. 1 block after the other. Make sense? So here we have 1 block after the other being processed. So when you go back to the analysis, here samples contains 1024 samples, for instance. Right? So we subdivide our audio signal into blocks of 1024 samples. First 1024, next 1024, and so on. So if we have a delay by 1, like z to the minus 1, that means we delay by 1 block, meaning 1024 samples. No? You look puzzled. Does it make sense?
Yes.
Okay. Yeah, so here in the D matrix is still okay, but then here with the D-inf matrix, this is not really the exact inverse, but it's the inverse including a delay by 1 block to be able to implement with the causal system. Yeah.
In the D matrix, we delayed the half of it. We didn't take the full of them. So when you ask the question, how many steps? But here you said n. But by the steps, it should be 2 steps, no?
Yeah. So
More
first,
than 2.
right. First, think about it. In the delay matrix D, you have the first half delayed. The second half is not delayed. What about D-inf? The inverse D matrix. Which is what we have here. Remember?
Second half.
Yeah. And the D-inf, we have the second half delayed, right? So D is the first half delayed, D-inf is the second half delayed, and we have the second half delayed because the exact inverse of the D would be first half advanced, so that we compensate for the first half delayed. But we cannot have the first half advanced, and that's why instead we have the second half delayed, so that both have the same delay. So over both D and D-inf, first we have first half delay and then we have second half delayed, which means we have an entire block delay. Right. So So that means over both D and dInf, we have one complete block delay. And yeah, that's the only one. The other ones don't really, over analysis and synthesis, they exactly invert. Right? There's no additional delay involved. The D matrix is the only one which has this additional delay to make it causal. Right? And that's why, yeah, overall, how much delay do we get?
1.
Yeah, 1, right? So, first block goes in. What comes out of the synthesis here in the first step?
The second one. The second one.
Yeah, so we will get the first block at the second step. What will we get in the first step? Well, zeros, right? Because our memory is initialized with zeros, so after the first step we get zeros out. Comes from an initialization. So then the second step, we will get the first block out. So we have to wait for one step to get the first block out. Right? So if you have streaming, then you also need to have n-1 samples to fill up one block. Right? So first you have to wait to fill up one block as n-1 sample, because at the last sample you can actually start right away. So you have n-1 plus n from this delay from the D matrix. So for streaming it would be a total of 2n-1 samples delay. Make sense?
Not really.
No? So where's the problem?
I didn't understand why 2 and 1 is 1.
Because in order to get one block, you first have to get samples from a microphone, if it's not in memory already. So if it's already in memory, like from a file, then it doesn't matter. But if you get those samples from a microphone or sound card or somewhere sample by sample, then you first have to wait until one block is full. Right? And that's why you get another block -1 as a delay. Right? But that's only for the case that you have to wait for the samples. If you have a file, then they're already in memory, and then you don't need to wait, you just need to access. Right? So then this doesn't count. Yeah, that's why you have to distinguish between those two cases. The case where you have samples arriving in real time, or the case where you process files. So for the case where system delay is important, when you have, say, telecommunications, you actually do have samples coming from the microphone, sample by sample. And in these cases, you really have this blocking delay. In cases you operate on files, delay doesn't really matter, because you already stored everything. Yeah. So now basically we are done with the function, and here we can do real-time audio processing. So here I actually used 512 bands because it's lighter on hardware, like slow laptops. So here I'm using capital N equals 512, and I'm loading coefficients which are already optimized from this file. Right? So these coefficients come from optimization, which I did before. So then I load it here, and let's see what's next. Here I'm using just the first 1.5 coefficients, because this file contains 2n coefficients for the F matrix. So it's just a slight difference in representation, so I compensate for this in this line here. And here this is a flag for the display. Display is true. Here I'm doing the initialization init filter bank, and I'm setting it to n subbands. Right? In this step, I zero all the memories and also determine the number of subbands. So now I'm actually running the filter bank here in these two lines. So you can see I have a for loop, in this case over 10 blocks. Right? So here I'm running the inverse low delay filter bank on some pre-constructed Y. So observe that this is just the inverse filter bank. Right? And this y consists of a 1.0 in channel number 0 at time step 0. Right? And then the rest is just zeros, as you can see here in the preceding line, 288. So basically I'm feeding the synthesis filter bank with an impulse to obtain the impulse response of the synthesis filter bank. And so this is for testing purposes. Here in this way, I'm getting the impulse response of subband number 0 of the synthesis filter bank. So it's kind of tricky to see if the filter bank has decent filters. Right? If it has decent filters, we will get some nice, smooth function out of it. Yeah, and then it's plotting the impulse response here. Right? And it also computes, with using Frexy, it computes the filter response, passband and stopband, so that we can see if we have a good passband and a good stopband, so that we can judge if we really have a good filter. Here it plots the dB. Right? So this is actually an easy trick for checking the implementation of the filter bank. Because remember, you can still have perfect reconstruction even if you have bad filters. Right? So this is one check here to check that you have good filters. So then I initialize the filter bank again because I now have non-zero values in it from this first test. And now I'm starting live processing. Here you can see I'm setting up the audio card. Here I open the audio card with a sampling rate of 32,000 samples per second. So this should be familiar with you, right? So here's the real-time processing. I have input through, output through, so there's a direct connection from input to output, but not direct with the filter bank in between. So here I'm also defining a waterfall diagram. Basically, we take the magnitudes of the MDCT of the low delay filter bank output and display it live as a waterfall diagram. And here's our infinite loop for reading the stream from the sound card. So here, data is read from the sound card. Next, it's converted from 2 byte to short integer, and then from short integer to float. Samples now contain our float samples. Here I'm detecting if we have an overload to avoid crashing the sound card. So this can happen if, say, I'm too close to the microphone, then it gives me an overload. Yeah, and this is for the waterfall diagram. Here it shifts the waterfall one row up, so that the lowest row is freed up for the next one, for the new one. Here is now the low delay filter bank. So here I'm taking the current samples, so 512 samples at this point, using the coefficients, and compute now the low delay filter bank coefficients. So no processing, so I'm directly going to the output. Now I'm taking those y-filled coefficients and display them in the logarithmic scale. Here creating some false colors so that they're easier to see, and then I display them here using imshow. And then after displaying, I'm computing the inverse filter bank here. I'm taking y-filled, inverse filter bank, again checking for overload to avoid crashing the sound card. Here I'm also clipping to avoid crashing the sound card. And then I convert back to bytes and write to the sound card so that we can listen to it. And I do that until I press the key Q. Makes sense so far? So now I can let it run using my Bluetooth speaker. Which hopefully works.
Bluetooth mode.
Sometimes it works and sometimes it doesn't. It's kind of tricky. So let's check sound settings. Hardware. Yeah, This looks promising. So, test figures. Oh yeah.
Front, right.
Maybe it's a little softer. Output volume.
Front, right.
Better? Okay. So that seems to work. So now I can let it run, hopefully. Let's see if it works. Python 3. Yeah, so this is the magnitude frequency response, and this is the impulse response of our filter bank. So remember, this was a test in the beginning. So here we put in the pulse, and this is the output of the synthesis filter bank, which for this case is the impulse response of channel number 0. It looks nice and smooth, right? And you can also see those additional ripples at the end, which comes from being a low delay filter. Right? It has this unsymmetric shape because it's a low delay filter bank. And when you look at part of our magnitude frequency response, you can see that it's actually quite good. Look at this axis here. This is just 0.1, and remember, it goes up to pi. Right? So this is actually 1/30th of my total frequency range, and we already get 60 dB of attenuation at frequency less than 0.04. So we indeed have a really narrow filter as desired. So this is really good. So this is actually quite a good filter. So we can be happy about this. So now we can close it. Maybe it was a little bit too loud. So this was a feedback loop that we had here. So let me try again. One, two, three. Wow. Quite powerful, huh? Yeah, it's okay. Output, maybe reduce the output a little further. One, two, three. This is the test. So you could see when it was yellow, that means the subband has a high output. Right? When it was bluish, it means an output had a subband had a low output. Right? So you could see that it basically did a nice representation of the spectrum. And now we can also try some changes of the subbands. Right? So now we could try this one here. So now I'm passing everything as it is. So now we could try a narrow band filter. So instead of passing this directly, we can make some changes. So first initialize everything with zeros and then just pass the subbands 10 to 150. So what frequency range is that? 10 to 150. What do you think? How would you compute it? So what frequency is subband number 10? Remember, we have 32,000 samples per second. What's the Nyquist frequency? 16,000, right? Half of it. So 16,000 is Nyquist, it's our upper limit of our frequency range. How many subbands do we have? 512, right? So I just said 512 here. So that means, what's the width of each subband then? Exactly. So each subband has a width of 16,000 divided by 512. So what's the result?
3125.
Yeah, okay, thank you. 31 hertz, right? So each subband is 31 hertz. So that means subband number 10 is what frequency?
300
Yeah, around 300 hertz, right? So what's 150? Yeah, I guess 4,500, right? So actually this one passes frequencies from 300 hertz to 4,500 hertz. Does that remind you of some range, frequency range? Like of telephone? What's the frequency range of a telephone? How much?
300 to 3,400.
Yeah, right. So roughly 200, 300 lower end up to about 3.5 kilohertz upper end. Right, that's telephone. So what's missing in telephone is a low range from 0 to about 200, 300 hertz, because the designers of the original telephone network wanted to save money. Right? So they said the lower frequency range doesn't matter for speech, because speech starts usually around 200, 300, and then the higher frequencies, they're nice to hear, but you don't really need them for intelligibility, so they stopped at 3.5 kilohertz, and that made their network cheaper, right? So it's only nowadays that in new DSL and digital telephones, sometimes you get a connection with much higher bandwidth. Did you notice? So sometimes when you call somebody on the same network, you will get a bandwidth of say 7 kilohertz, and then it really sounds like the person standing next to you, right? Because it's much clearer. Yeah, so this then should sound more or less like a telephone. So let's try. So we only keep subbands in this range. So again, analysis here. This is a test. 1, 2, 3. Then you get feedback. Maybe I reduce it a little bit more here. Oh, I can actually change the volume here too, I guess. This is a test. Ah, so this is much better. Test. Oh yeah, this works. This is a test. 1, 2, 3. 1, 2, 3. This is a test. Can you hear that it sounds more like a telephone? And you also see it when you look at the waterfall. You only have this narrow part here instead of everything. Here, the blue is all set to 0. This is not transmitted to the decoder, to the synthesis filter. So high frequencies are missing, low frequencies are missing, and this is how you get this telephone speech characteristic. Okay. Interesting. Huh? So, yeah, this shows that we actually have good filters, and we can do many interesting tricks. So another trick is to just listen to one individual subband. So what do you think? How will one single subband sound like? So now we have subband number 30. 30 is what frequency? Yeah, maybe 1 kilohertz, right? A little bit less than 1 kilohertz. Yeah, what do you think? How will it sound? You have a bandpass, a very narrow bandpass, it's slightly less than 1 kilohertz. What's your guess? Any idea? Imagine it's just 30 hertz wide.
Something noisy, like some beep.
Yeah. Is 30 hertz enough to understand speech? No. it's not, right? Because telephone is already as narrow as you should make it. You cannot really make it much more narrow without sacrificing intelligibility. So 30 Hertz here is by far not enough to understand speech. And yeah, I expect something like a noisy beep, right? Because just a slow fluctuation. Yeah, I'm here already hearing something. Very good. So let's try. Right, this is how it should sound like. This is a test. 1, 2, 3. 1, 2, 3. Test, test. So there's no speech coming through, right? 1, 2, 3. Just a beeping sound which varies. And you can also see, when you look at the spectrogram, there's only one line here. Right? This green line here. That's all that's left. Very narrow. Interesting, huh? So one subband is not really enough to do something useful, but all subbands together give you the complete audio. Right? Imagine that your speech or your audio can be decomposed in many of those beeping tones, and if you mix them all together, you have music or speech. It's kind of amazing. So you can basically decompose everything into those tones. Okay. Okay. So, yeah. Go back to the original setting here. Yeah, so here you could see the implementation and that it works. And here you can see a few examples of low delay filter banks. Right? So here's a comparison having 128 subbands, and you compare it with an orthogonal filter bank, an MDCT type filter bank, with filter length 256, which is the dashed line here. So this is an MDCT type filter bank. And then the solid line here is a low delay filter bank with a length of 512 and a delay of 255. So the same as the MDCT type filter bank. This delay includes the blocking delay, right? Because the cases where the delay is relevant is also the case where we have individual samples arriving from the sound card. So that's why you include the blocking delay. Yeah, and you can see here, we differ in this tail. So here you can see the tail of the low delay filter bank is continuing much more than for this MDCT type orthogonal filter bank. And this tail doesn't look like much, and it's actually tiny ripples, but those tiny ripples make a big difference, as you can see here in the frequency response. So here you can see the stop attenuation of this low delay filter bank is about 20 dB better than the MDCT type filter bank. So it actually gave you a big benefit here in the performance of the stop attenuation. Yeah, and you can also use it to prevent or reduce pre-echoes, because the low delay filter bank only has ripples into the past, basically. And that's why you can avoid pre-echoes, which result by having a window which looks too far in the future, right? And to make it look more in the future, you need more delay. So that's also a way to look at filter banks which are longer but also have more delay, MDCT type filter banks. They look more in the future, and that means when you have a sudden attack coming up, then this attack from the future influences the present coding performance, increasing the noise. And this is actually then leading to so-called pre-echoes, which means noise from the attack in the future will be heard before the attack. And the ear is very sensitive to such noise, and that's actually a problem in audio coding. If you have too long block length or too long filters, then this will appear. Right? So this is a typical artifact which appears when you use castanets or something similar. So what's done is then, instead of having the same block size, say 1024 all the time, you detect that there will be an attack coming. And when you see this attack coming, you switch down to shorter block length. So here in this case it's 128 samples. So here you have 8 times 128 samples, so that's again a block of 1024. So this block of 1024 is subdivided into 8 smaller blocks. And since we have smaller block sizes, that means we accordingly have to reduce the number of subbands also to 128. Right. So that's the downside. If we have a higher time resolution in this way, using finer blocks, meaning we have a higher lower sampling rate, that also means we have fewer subbands, meaning less frequency resolution. And less frequency resolution means less possibilities to save bits in compression. So that means we avoid pre-echoes, but at the cost of an increased bit rate. And that's why this is also kind of tricky. You don't want to do it too often. You can do it from time to time, when you have a buffer for the bits, for instance, but you don't want to do it too often to keep the increase in bit rate limited.
Which is this signal is pre-echo or just it's pre-echo?
Yeah, in the previous you could see the pre-echo, you cannot see it here. So this is the pre-echo. This is basically coming from spreading the quantization noise to before the onset.
That's why there is no this echo. But
Yeah.
So why do we need to like?
So this is the diagram of the input signal. Right? The input doesn't have pre-echo. What you just saw on the previous slide was the output, including the pre-echo. So here we want to avoid the pre-echo. So in this case, here you can see those short blocks. The pre-echo would only cover this block, right? Because this is the amount of looking ahead. So here you have the next block. Here you would increase the quantization noise, which would then also spread here. So here you would have a much shorter pre-echo, right? As opposed to this entire block of 1024. Yeah.
How we will see that there will be pre-echo from
You guess, basically. Yeah, so here you can see basically this is spread over the entire preceding block. Right? Because your window length, your impulse response length is 2 blocks. Remember, MDCT has 2 blocks. So if the attack enters 1 block, then the resulting quantization noise is going into this block and the previous block. Right? So that's bad. Here it's better. Right? This block and previous block, it's short enough that the ear doesn't notice. That's the so-called network mask. Right? Because the ear also has only a limited temporal resolution. And if some noise comes close enough to the attack, the ear cannot distinguish those 2 events anymore. Remember, the ear basically is also doing filtering. It is a filter bank with unequal bandwidth. So it actually has a very fine time resolution. But here in this case, you keep it small enough that the ear doesn't notice. Makes sense? So that's why you want to do block switching, to avoid pre-echoes. So the ear towards higher frequency has filters, remember? The cochlear filters. When you go to higher frequencies, they have higher bandwidth, but also higher time resolution. So they become wider and wider towards higher frequencies, like in the bar scale. But wider bandwidth also means higher time resolution. And that's why the ear can be very sensitive in the time resolution in attacks like this, because attacks are quite broad in frequency. They cover a wide frequency range, including the high frequencies, where the ear has very high time resolution. And that's different with the MDCT. The MDCT has the same bandwidth at the same time resolution for every frequency band. Basically because it's easier to implement in this way. And because of this difference to the processing in the ear, you have to do the switching here. You have to look ahead into the next block in the encoder, and if the encoder detects an attack in the next block, it then signals the filter bank, now you need to switch to a lower number of subbands and shorter blocks. Make sense? Yeah, so it's basically a simple fix for this problem of a non-fitting filter bank to the cochlear filter bank. Yeah, the way this transition to shorter blocks is done, despite the overlap, can be seen here. So remember, in the MDCT, we have two windows of length of 2 blocks overlapping the 50%. That means the first window and the next window overlap, and you also need this overlapping in the synthesis to do the reconstruction. They need to add up in order to cancel aliasing and also in order to get the perfect reconstruction, which is basically the same. So here you can see this overlap add is adapted. So in the beginning, you have the same shape as before, but then in the second half of the window, you end with shorter blocks. So here you have this ending, which looks like from the shorter block, and then you actually switch to a filter length with the shorter blocks next, which then fulfills the overlap add again for perfect reconstruction. Right. So this is basically how the switching is done. So you have a window, which is called start window. So here it has the round beginning, then it has a sequence of ones, and then here it looks like the short window of 128 subbands near the end of a short window. And then here you have a normal 108 subbands short window, and so on. And switching back, you go the opposite direction. Right? You have a long window which starts looking like the short window, and then it continues like a long window. Make sense? Yeah, so here is how it looks like. So here's the time axis. Here you have the sequence of windows. So remember, each window covers 2 blocks. Okay, so here is the first block, here you have the second block of 1024 samples. Right. So here's the window covering 2 blocks, and then 1024 sub-band samples are computed. Here's the next window. Here also 1024 sub-band samples are computed, the next set. Right. Remember this waterfall diagram? Each time I have a new entry in the bottom, it's like from the next window. Make sense? So except that this window here ends like a short window would end. So here you have, in the beginning it looks like a normal window, then you have the sequence of ones, and then it ends like a short window here. And then what follows is a sequence of short windows with the same overlap and add. And here you switch back with a long window that looks in the beginning like a short window, then it has a sequence of ones, and then it continues to look like a long window with 1024 subbands. So here, for each of those blocks, you get 128 subbands. Here 128, 128, and so on. Until you're done, and here you again get 1024 subbands, 1024 subbands, and so on. Make sense? It's easy, right? If not, you have to ask. So this is how you would do the switching. So does this diagram make sense to you? There's a sequence of windows.
No, it's hard. Maybe you can repeat.
Yeah, ask me, what's the problem?
It looks strange.
Yeah, in what sense?
This constant overlapping between functions.
You mean this part here?
It's like so many crossings.
Yeah, this is because here you have many windows. That's why you have many crossings, right? Remember from the program, you have a sequence of blocks coming in. Right? For each block coming in, each block 1024 samples coming in, you have 1024 subband values coming out. Remember? And this is also what makes this spectral waterfall. For each 1024 subband coefficients, you get one row of this waterfall spectrum. And you get about 31 per second.
So in the middle here, where we have a higher frequency of changing, is we change from 124 sample subbands to, for example, from 1000 to 100. So we change sampling rate.
Yes, exactly. So here you have 1024 subbands. So for each block of input of 1024 samples, you get 1024 subband samples. Here, for each block of 128 samples, you get 128 subband samples. So instead of 1024 subbands, you only have 128 subbands, which correspondingly have a wider bandwidth. So the bandwidth is also 8 times as high. So instead of 31 hertz or something, we have 8 times 30, so like 250 or something hertz bandwidth. Yeah, and that's indeed a major change. We changed the resolution. Yeah, so does this diagram now make more sense? Or are there still questions?
So in the middle, we have more information.
Not necessarily more information, but different information. Right? Here you have only 128 subbands, but you have more of them. I mean, you have more a long time, so they appear more often. So you have only 1/8 of the coefficients in the frequency domain, subband coefficients, but you have them 8 times as often over time. So this is basically just a different time frequency resolution, where you have lower frequency but higher time resolution. Here in this region, you had a high frequency resolution but a low time resolution. Because it's long blocks, it means the time resolution is correspondingly low. Here you have short blocks, which means you have a higher time resolution, because those blocks are shorter, so they come more often. But as a result, you get lower frequency resolution. So time resolution times frequency resolution is always constant, like in quantum physics. Right. Makes sense? Yeah, and then I mentioned that the cochlea has unequal frequency resolution, and this can be to some extent mimicked by wavelets. Wavelets basically use this tree structure, which we successively refine the frequency resolution for lower frequencies. Right? Cochlea is doing the same. It has high time resolution and high frequencies, and high frequency resolution and low frequencies. Here we do the same. So here we have a wide filter, this high pass, and we only downsample by a factor of 2 instead of 1024. Right? Remember, MDCT would have 1024 as a downsampling rate. Right? Remember the 1024 downsampling rate? So each subband filter had the same downsampling factor. 2024. Here we only have a 2, so that means we have almost the same sampling rate as the original. But then the low pass here, we continue to subdivide. Right? So here we have another 2-band filter bank. Here then we keep this part here, which effectively then has a downsampling of 4. So here's 2 and then there's another 2, so we have downsampling of factor of 4. Same here, but here we continue to subdivide. So for the low frequencies, we continue to subdivide in this tree structure, which means we double the frequency resolution or the narrowness for the lower frequencies in each step. Yeah, and for that we need this 2-band filter bank, and those 2-band filter banks have the problem that, relatively speaking, their transition band is too high. Right? It can easily be as high as the stop band. And that's why here a different approach is taken to design 2-band filter banks, which have really narrow transition bands and still good stop at attenuation. So here's the polyphase representation of a 2-band filter bank. So just 4 elements. You may still remember polyphase. So we have 2 phases and 2 frequencies. Right? So the first index was phase, the second index was frequency. And each of those entries is the downsampled and Z-transformed impulse response. First column, downsampled low-pass filter, and second column, downsampled high-pass filter. And here, downsampled with the 2 phases. First starting with 0, second starting with sample number 1. And then the result is Z-transformed. Yeah, so H00 then contains the even coefficients of the low-pass filter, and H1, 0 is its odd coefficients. Right. And accordingly for the high-pass filter. Yeah, and since it's simply 2 by 2, we can easily compute the inverse. Right. So the inverse simply consists of flipping the diagonal elements and changing the sign of the off-diagonal elements, and then divide everything by the determinant of H. Remember this formula? So this is a simple trick for 2 by 2 matrices. Yeah. So if the analysis filters have a finite impulse response, FIR, and the synthesis is desired to be also FIR, then the determinant of the polyphase matrix also needs to be a constant or a delay, otherwise it becomes IIR. Right? Remember when we have an IIR filter, we have a denominator polynomial, and in FIR filters we have no denominator polynomial. Remember? So that's why basically this determinant is a problem. But we want to get rid of it. It should be either a constant or a delay. Yeah, and when we look at it, this is the formula that's now constrained to be a constant or a delay. And when we look at this formula, this is the output of the lower band of the filter bank if the input signal X consists of these Z-transforms. Right? And hence the determinant can now be formulated as a convolution. Right? It's the input. So if this is the input, give it into this filter bank, then the output gives you the determinant. So when we look at it, the input is the high band coefficients with the sign of the even coefficient flipped and switch places with the odd coefficients. So maybe that gives us a solution. Yeah, since this represents a critical sample filter bank, the result represents every second sample of the convolution of the low band filter with the correspondingly modified high band filter. And this modified high band filter is a low band filter. When you do the flipping, the high band becomes a high pass becomes a low pass. Remember, every second sign of the impulse response is flipped. That basically turns a low pass into a high pass or a high pass into a low pass. So here we turn the high pass into a low pass, put it into our filter bank, and the output is our determinant. Yeah, so the desired output of this downsampled convolution should be a single pulse corresponding to a constant or delay, and hence flat in frequency. Or another interpretation, correlation of the two signals where the even lags appear after downsampling are zero, except for one pulse. Right. Yeah, so this should just a simple design strategy. First obtain a low pass filter for analysis and synthesis. Then obtain the corresponding high pass filters by flipping the low pass filters every second coefficient, as you can see here. So now we obtain the high pass filter using sign flipping. Then the high pass here doesn't really fit. It should be G0, H0 are low passes. Should be synthesis. Synthesis. So this should be low pass. Synthesis, low pass. Funny. Okay. So, and this should be the synthesis filter bank high pass. Okay. Okay. Yeah, so this is an early two-band filter bank called the Phototron Mirror Filter, QMF, from 1976. And you can also try this with more than two bands, and it's called Generalized QMF, GQMF. Yeah, so sign flipping to obtain the high band leads to these polyphase components, and that means the resulting determinant is this. And here we can see that this cannot be made constant or delay for finite polynomials of order 1 or greater. Hence, there is no perfect reconstruction for finite length filters. So that's kind of disappointing. Right? You get a somewhat decent filter, but no perfect reconstruction. So this is what you should actually keep in mind. There's a problem for perfect reconstruction. Yeah, so the QMF accounts for the sign flipping in the determinant equation, but not for the trading places of even and odd places in the determinant. Hence, there is no perfect reconstruction. So high slot attenuation is needed to keep reconstruction error small, and hence we use numerical optimization to obtain this equation here. So magnitude of the low pass filter plus the magnitude of the high pass filter should be approximately 1. So basically, if you add those frequency components, you have a flat frequency response. So at least this is desired, that you don't change the frequency response. So that looks like this. If you add those two, then they should add up to 1, right? Which is the case in this simple diagram. Yeah, and here's an example of the QMF with an impulse response of length 96. This is the low pass impulse response, and this is the high pass. And you can see for two-band filters, they are quite normal. Right? Remember, for the MDCT, we have a filter length of 2n, right? Twice the number of subbands. On low delay filter bank, we had 4n or 6n. So here we have 96. So how many n is that for n equals 2? 96 tab is how many n here? How big is n here? N is 2, right? 2 subbands. So the filter length is how many times our subbands? And what is 96 divided by 2? 48, right? So we have 48 times n. So that shows a big difference to the approach we took for the MDCT. For the MDCT we have only 2 times n, or for low delay filter banks several times more n. But this is like a whole other order of magnitude. We have 48 times n. Right? And this means we get very narrow transition bands and hopefully still good stop at attenuation. Right? And that's the advantage of this approach. We sacrifice perfect reconstruction, but we get extremely good filters. Yeah, but that can be improved with a simple step of flipping the ordering of the high band. So instead of just having the sign flipping, we now also flip it in time. We apply a flip LR to it, to the high band. And then we also take advantage of those trading places of the even and odd coefficients. So here we have the corresponding filters. And this is introduced by Smith and Barnwell in 1984. And when you plug it in, you get this formulation here. So basically, the input for our determinant calculation is then this, and this corresponds exactly to the time reverse low band filter. And that actually then leads to perfect reconstruction. So here, the determinant now can be seen as 2 polynomials which are added. And this can be a constant at all even coefficients of A of sigma 0, except for the center coefficient, because it's flipped to itself and you add it. And that works if everything is 0 except for the center coefficient. No. Right. So the determinant was the output of the lower band with its input, and every second sample of the convolution of the low band filter with its time reverse version. And this is equal to every second value of the autocorrelation function of the low band filter. So that means the determinant is constant, or delay means only one sample of this downsampled autocorrelation function, or all even coefficients, can be unequal 0, which means most even coefficients are 0. So this gives us a recipe for designing filters. Yeah, and I guess time is up, so maybe I'll continue here next time. So thanks for your attention and have a nice evening.